Hello all, in this lesson we're going to be studying for the Unit 9 exam. So let's go ahead and get started with this graphing question. So an investigation was conducted to study the effect of the concentration of a reactant on the total time needed to complete a chemical reaction. 4 trials of the same reaction were performed. In each trial, the initial concentration of the reactant was different. The time needed for the chemical reaction to be completed was measured, and the data for each of the 4 trials is shown. So there's the data right here in the graph, and we're basically just being asked to plot. So one of the things you can see is that the initial concentration goes from 0.02 down to 0.005, and it's also labeled here on the x-axis, and the reaction time is increasing as the concentration decreases. So I'm going to plot these data points in now. I've decided to make every one of the blocks on the y-axis be equal to 4 so that it'll get me to 60, which is a little bit larger than my largest data point. And I can plot the data now. So there are my data points, and I'll go ahead and connect them with a line. So one of the things I'm noticing is as the concentration increases on the x-axis, you get a reduction in the reaction time, which is equal to an increase in reaction rate. So let's see how all of that holds up in our short answers. In a different experiment involving the same reaction, it was found that an increase in temperature increased the rate of reaction. Explain this result in terms of collision theory. Well, if you increase the temperature, you're going to increase collisions, which would increase the rate of the reaction. For number 2, A and B, I went ahead and did all that already. For number 3, let's state the effect of the concentration of the reactant on the rate of the chemical reaction. So I just noticed earlier that as the concentration increased, the reaction time decreased, which is an increase in the rate. Next up, which list of the phases of water is arranged in order of increasing entropy? Gases have the most entropy because they have the most chaos, so I think the best answer choice is 2. Number 5, given the reaction at equilibrium, which change will not affect the equilibrium concentrations of A, B, and A2B3? Well, adding a catalyst will increase the rate of the reaction, and it will reduce the time needed to reach equilibrium, but it doesn't actually shift the equilibrium. Next up, given the reaction at equilibrium, what occurs when the concentration of hydrogen is increased? So if we increase the concentration of hydrogen as our initial stress, and then we can outline in blue what happens as a result. So the initial stress was positive. I added hydrogen. Le Chatelier's logic says that the reaction will try to remove the hydrogen, and the only way to do that is to increase the rate of the forward reaction in order to react away some of the stuff on the left. So when you increase the rate of the forward reaction, you're going to make more ammonia and more heat, but you're going to be using up the hydrogen that you just added in, and of course using up nitrogen as well. So let's see which one of the answer choices jives with what we've shown here. Fortunately, it looks like I don't have to read any farther than choice 1. The rate of the forward reaction would increase as indicated, and the concentration of the nitrogen would decrease. Next question. Given the reaction at equilibrium, what would be the result of an increase in temperature at constant pressure? So initial stress in red, so the initial stress is to increase the temperature. Le Chatelier's logic says that the reaction will try to reduce the temperature, so the only way to do that is to speed up the forward reaction, the one in which temperature is a reactant. So if you speed up the forward reaction, you're going to get more of this nitrogen dioxide, and you'll be using up the heat and using up the dinitrogen tetroxide, which would both be required to make the nitrogen dioxide. So which one of these answer choices makes sense for that analysis? So when the reaction is shifting to the right, we know it's going to be choice 3 or 4, but also we know that the concentration of nitrogen dioxide will increase because it's shifting to the right. Okay, which factors must be equal in a reversible chemical reaction? So in reversible chemical reactions, at equilibrium, the things that are equal are just going to be the rates of the forward and the reverse reactions. And a solution that's at equilibrium is always going to be considered saturated. Here's why. It's because if you look at this diagram, you can see that there are particles who are recrystallizing, like these two, and there are particles that are dissolving, like those two. Overall, you're not going to notice anything happening to the pile at the bottom of the flask, but it's also saturated, and that means that you have equal numbers leaving and coming down, and overall the dissolving process has come to a halt. All right, ammonia is produced commercially by the Haber reaction, and the formation of ammonia is favored by which of the following factors? So this is a gaseous system, and in gaseous systems, the number of molecules on the left and the right can matter. Like for instance, you have 4 moles of molecules on the left and 2 on the right, which means that if you increase the pressure, it's going to want to shift to the side that takes up the smallest amount of space, which of course is the right-hand side, or where the ammonia is. So if you increase the pressure, you will be increasing the formation of ammonia. In number 11, we want to know, given this balanced equation, which statement is true about energy. So you can see that the energy is over here on the right-hand side of the equation, which means it's a product. And it also means that the reaction is exothermic. So that leaves us with basically choice 1 that we can choose. Next question is number 12. Which expression represents delta H for a chemical reaction in terms of the potential energy of its products and reactants? So the two types of reactions where you might come across this are exothermic on the left and endothermic on the right. And if you look at the difference in energies between the reactants and the products, in both cases you're going to get the delta H. So the delta H is just the difference between the product's reactant energy and the reactant's energy, or as labeled here. So delta H in both cases. That's potential energy of the products minus potential energy of the reactants. Choice 2. All right, at number 13, we want to know which beaker would have the fastest reaction rate. So the things that are being altered from one beaker to the other are temperature and concentration. What I can tell you for sure is that an increase in concentration will increase the rate of reaction, and increasing the temperature also increases the rate of reaction. That's why beaker D would have the fastest reaction rate. So in addition to concentration and temperature, also the preparation of the substance matters, such as powdered with large surface area is going to be a faster reaction rate than, let's say, solid with a smaller surface area. So at STP, the 4 grams zinc sample that would react fastest would be the one that's powdered. In 15, we're asked about a catalyst, and it says adding a catalyst to a chemical reaction results in which thing? Of course, it decreases the activation energy, but by decreasing the activation energy, you get an increase in the reaction rate. And that's because it basically has to spend less energy sort of getting over that hump, and you can take this alternate reaction pathway and it makes the reaction speed up. After being ignited in a Bunsen burner flame, a piece of magnesium ribbon burns brightly, giving off heat and light. Now, in this situation, the Bunsen burner flame provides the activation energy. It's allowing the reactants to get enough energy to collide with the proper energy and then go through their reaction. 17. In most aqueous reactions, as temperature increases, the effectiveness of collisions also increases. I think that one's straightforward. 18. Two reactant particles collide with proper orientation. The collision will be effective if the particles have sufficient kinetic energy. So they have to be moving fast enough and at the right speed in order to have an effective collision. Number 19. Which conditions will increase the rate of a chemical reaction? Increasing temperature would always be a good thing, and also increasing the concentration of the reactants helps as well. In both cases, these two guys are increasing the number of collisions. Now, beaker A contains a 1 gram piece of zinc, and beaker B contains 1 gram of powdered zinc. So we're already thinking this one might be a faster reaction. But it goes on to say that if 100 milliliters of 0.1 molar HCl is added to each beaker, how would the rate of A's reaction compare to the rate of B's reaction? So since B is powdered, it should be faster. So let's say that the rate in B is greater due to the larger surface area of the zinc, or choice 4. 21. Which arrow represents the activation energy of the forward reaction? So the forward reaction is the one that goes in this direction, and the activation energy is the difference in energy between the reactants and the activated complex. So that is interval B in this case. 22. We have another diagram, and they want to know which arrow represents the potential energy of the reactants. So here are the reactants, and their potential energy is marked here on the y-axis, but you would measure it by looking at the difference between 0 and the reactants. So that's B. At STP, a sample of which element has the highest entropy? In this case, one of the things that really sets the answer choice 4 off as being correct is that it is in fact a gas, and gases have the most entropy of all the phases. Going further for the last question, in number 24, the temperature at which the solid and liquid phases of matter exist in equilibrium is called its melting point. So this is a type of phase equilibrium. The other one would be at the boiling point, where you have an equilibrium between liquid and gas. But at least between solid and liquid, that's the melting point. And 25, given the system at equilibrium, which change would not shift the point of equilibrium? So this is an all-gas system, and one of the things you should check for when you're dealing with all-gas systems are the number of moles equal on the left and the right. In this case, they are. I see 2 moles on the left and 2 moles on the right. And that does matter because this means that changing the pressure would not actually affect the point of equilibrium. So my answer is actually choice 1.